Hello everyone. In this video, I'll be presenting results from this paper titled MOPO, which is a model-based offline policy optimization. So this work is on offline RL. So the authors are from Stanford University and UC Berkeley, and yeah, Sergey Levin, Chelsea Fenn, and Tenguma, all three professors have um contributed to the RL community with so many works. So, yeah, this is one of the new works which was published in 27th May 2020 on offline RL. So, yeah, let's get into this paper, the main content of this paper at least. So, I'll begin with the abstract as usual. Offline RL, as usual, it is the problem where we learn policies based on previously collected data instead of interactively collecting data with the environment. So, yeah, this problem, as usual, is compelling. Uh, it offers promise of utilizing large, diverse, previously collected data sets. But yeah, as usual, we have many difficulties like distributional shift between the offline dataset and the learn policy. Yes, this is the usual terminology which we saw in the previous video which I made on D4RL. So, which is essentially the paper which builds the dataset required for offline RL benchmarking. So yeah, you could go and see that. I'll put a link to that video here. So now continuing with this, in this paper we observe that existing model-based RL itself has significant gains against model-free approaches, which is really a good observation. Yeah. Does this mean that there is no further use of model free? No use of model free further? Let's get into this draft. Yeah. So, provide a mechanism to avoid the issues associated with. Okay. Yeah, I mean, the current model based don't address these issues. So what this paper does is give a fix to this using the penalized MDP approach, and yeah, maximizing the lower bound in the return. So basically, one could say that we have a return RM star for the true MDP, but we can't access this, but we can get a lower bound with respect to some known MDP, M tilde, which is the penalized MDP which they are talking about here, plus or minus some constants which we will discover further, and maybe increasing RM tilde, yeah, will achieve the purpose of, I mean, hopefully that will make it reach RM star. Yeah, this is the just the view from this abstract. So let's go read it further. Yeah, the offline algorithm, the variance of a Lipschitz regularized model has a penalty. Okay, reward is penalized. That is how the penalized MDP name comes from. So yeah, um, let's get into the introduction section right now. So, well, of policy, RL algorithms utilize, they perform poorly on online data collection. Yes, this is observed in these papers. You can see it later. I'll link to this paper as well. So, yeah. Some reason for these failures could be extrapolation error when Q function is evaluated on out of distribution actions. Let's see. So I know what this out of distribution uh, might be. Let's see. I can summarize this out of distribution in this way. Like, let's say distribution induced by the learned policy and by the data set itself. So these two are not same in this offline setting, so this might rise the extrapolation error. So yeah, one could expect an naive result such as, like, if M star, the optimal MDP, and the MDP which is induced by this data set are the same or close to each other, then one can expect this error, extrapolation error, is close to zero. Yeah, this we can expect this. Yeah. So moving on further, it says so wide range of offline RL algorithms proposed mitigate bootstrapped error by dataset. So this is just saying that we keep pi close to the dataset policy, which usually this group calls it as a behavioral policy or pi b. But yeah, this is like the similar formulation as in imitation learning. So yeah. So yeah, specifically these methods estimate error with respect to out of distribution actions, but do not consider out of distribution. So it's like they only look at state action pairs which are in the data set, and they don't actually look outside of this region. So yeah, this might be very limited to this behavioral policy space. So yeah, so now they further say along these lines that we argue that it is important for offline RL to be equipped with the ability to leave the data support of behavioral policy, provided data batch data set is usually suboptimal. Yes, so that is why we need to explore more. I mean, the explore term here is just to go outside of the support of the data set, so not the usual exploration term which I'm talking about. So the second point is that the task can be coming from different multitask oriented batch data set. So yeah, so we cannot actually use it like how imitation learning assumes. So yeah, so that is why can we develop offline RL algorithms that generalize beyond the support of offline data. So now towards this, they further mention that firstly model based RL algorithms effectively receive more supervision. Yes, we are approximating the model itself. So yeah, this is an advantage for better supervision from the data set. Okay, so this is one thing which they observe. Yeah, I mean they are trained using supervised learning, which provides more stable and less by bootstrapping. Okay, yeah, that is true. Bootstrapping has its own bias invariance estimations, bounds associated with that. Yeah, so and lastly, something called uncertainty estimation techniques, such as are well developed for are poorly performed for value based RL methods. Yeah, I mean we have to I don't have much idea about the third one which they say, so we'll have to probably more look into these references. So let's go forward from here. Yeah, as a proof of concept, we evaluate two state-of-the-art off-policy model-based and model-free algorithms, MBPO and SAC. Okay, although neither is designed for batch setting, it is, they observe that MB model base is better than MF here. So yeah. This seems a good observation. Okay, offline model-based algorithms cannot improve the dynamics model using additional experience. Yes, that is the requirement. We expect such algorithms require careful and calculated models in regions outside the to achieve. That is, we are moving away from the support of the data set. So to do so, we modified MBPO to incorporate a reward penalty based on the estimate of the model error. Okay. So yeah, so the penalties are made dependent on the errors between m and some function of this, some error function of m and m tilde, in the hope that this will let the algorithm explore S&A which are not in the data set. So yeah, moving forward, in a penalized model MTP, where reward function is penalized by estimate. Yeah, here this is the important thing. Lipschitz regularized model uses this uncertainty estimate as the reward penalty and trains a policy using MBPO in this uncertainty may penalize MTP. So this is some kind of bounded constraint optimization. So yeah, let's see forward how it goes. Okay, here they mention one more important line, that find the optimal trade-off between return and the risk. Okay, yeah, I mean need to balance between the reward, max reward, and the penalties, so that we get good policies in the end. And yeah, as usual, they test these algorithms on the benchmark data sets created in this D4RL paper. So yeah, let's move forward to the second section, related work. Okay, so here, well, many offline algorithms can in principle be applied. Yeah, they perform, as we saw earlier in the previous section. Now model free offline RL. So yeah, the two ingredients which it uses is constraining the learned policy to be closer to. Okay, this is again similar to imitation learning, which comes in model free offline RL algorithms very implicitly, I guess. So yeah, applying uncertainty quantification techniques such as ensembles to okay. I don't know what's the effect of the second point, which is not so clear here, so let's keep it as it is and move forward. Furthermore, we utilize to quantify the risk, leaving the behavioral. Okay, so it's like so the second point is more towards dealing with the difference of policies from the algorithm and the behavioral policy. So the difference, so model based online RL. This is the first paragraph is on the online part of the RL. So we already saw that the interactions don't help further. So yeah, let's move to the second paragraph. Okay, so here there is a concurrent work by Kitambi et al. So which we can look at. If I make the video, I'll just put a link to this, so you can view that paper description. So yeah, so their algorithm is called model. Maybe it is like model based offline reinforcement learning, I think so. Model based offline RL, maybe this is the acronym here. So let's move forward. So what they say is model uses hard thresholds, and here MOPO uses the soft reward penalty. So maybe my guess would be that like the next state is t plus 1 you may be forced to an absorbing state. Whenever the difference between pi b and pi is greater than some threshold. Yeah. Here, the softness in MOPO comes from this part being implicitly carried into the reward as we are penalizing it. So let's move forward. The third section, preliminaries. So the initial part is the usual definitions of MDP. Okay, so here the transition probability matrix is represented by T. Usually people avoid using T. I mean, if you are using something similar to operators, so usually people just prefer P over T. So yeah, let's use this symbol T as the transition probability matrix. I'm so used to T being Bellman operators, so sorry if I make a mistake and moving on. So yeah, let's see. T is the transition dynamics, R is the usual reward function, mu naught is the initial state distribution, gamma is the discount factor. Okay, so value function is conditioned on this initial state, so taking an expectation on different possible starting distributions will give us the eta m of pi, the expected discounted return. So yeah, in offline RL, the data set DE, okay, the NVs are generated by one or more behavioral policies pi b. We refer distribution from which T and V. Okay. Yeah. Now model MDP is replaced with T hat. So the reward function is assumed to be known. So yeah, which is done usually in the current RL papers. So we just concentrate on P being unknown. The same techniques can be applied if R is unknown. So yeah, it is just easier for this assumption to be made. So now they define peak by T. Okay, this the superscript subscript things as probability of being in status at time step T when actions are according to pi, and okay, transitions. Okay, this is a lot of notations here, but yeah, we can process this. Yeah, this row is the discounted state distribution. Okay, this is the usual long-term state distribution formulae. So by abuse of notation, okay, so okay, this is the state action distribution. This okay, makes sense. Yeah, I would write this as like this might not be the distribution, so I'll just write it depends on the product. So yeah, I mean, you could say this is equal to the numerator divided by the partition function z, which is the partition function z is nothing but if this is discrete SA, so yeah, the numerator term with SA day. So now there is this claim. I guess this is obvious, but yeah, informally I can write this down somehow. Let's see, eta m hat of pi is equal to 1 minus gamma times square gamma party by given as divided by this partition function, which can be written as blah 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 r of SA. I guess these two get cancelled, and you could treat maybe, yeah, this part as the probability distribution. Let's see, yeah. So yeah, I could club them together and write it down as an expectation under this distribution, and yeah, write this. Okay, we can just consider this as well. So yeah, R of SA. So yeah, I mean, this was very informal, but yeah, you could look at some books like Bertsek's Dynamic Programming and Optimal Control book, or Martin Putterman's book. So yeah, let's go forward. Yeah, here they summarize MBPO, which is the crux of this MOPO algorithm as well. So yeah, let's see. MBPO learns a model of the transition distribution, okay, by parameterizing it by theta. Yeah, behavioral data D and V also learns a model the same, yeah, which we are skipping it here, this reward function thing. Yeah, usually this D model is updated by the learned policy, the data, and then again the loop is repeated. Yeah, here in MOPO, the offline setting, yeah, okay, that is the D model updation is skipped. So yeah, MBPO performs surprisingly well. Okay. Yeah. So moving forward towards the results, the main results, theoretical results of MOPO. Yeah. This concern is especially important where mistakes in the dynamics will not be corrected with additional data. Okay. To balance return and risk, potential gain in the performance by escaping behavioral and risk of overfitting the errors of the dynamics at regions far away from the, yeah, you should get the balance somehow. So yeah, this section is split into the first part being in section 4.1 and the second part being in section 4.2. Okay, practical implementation of the algorithm is in section 4.3. Let's go forward. Quantifying the uncertainty from the dynamics to the total return. So yeah, glancing over this lemma 4.1, yeah, this is what I had written initially. So what this is saying is, for any pi, policy pi, expected return of m is greater than or equal to expected return of m hat minus some constant times the error function of m minus m hat. Yeah, we should further look how this is being controlled. Let's go forward. Yeah, this is obvious, right? I mean, if m is equal to m hat, the error is 0. So yeah. So yeah, here it is being generalized to much richer class. So the error function. Earlier this was a value function, so here if we consider any bounded function which is in this class f, we could write it in this way. Yeah, we could bound with the supremum norm of this function class. So yeah, this seems a good metric for this for quantifying this error. So they give two examples for this function class. One which makes this df to be the total variation distance, and hence we could write it in this way. And the second one is if being the one Lipschitz function, which would just give us the one Wasserstein distance and with some Lipschitz constant of which comes from this v pi. So yeah, the same. Yeah, from 4 and 5 we could make this assumption 4.2, which makes sense. Yeah, and from 4.2, I mean the assumption 4.2 will lead us this the characterization of this error. So yeah. Now moving forward a bit. So further you can assume this df is bounded by the uniform function u of sa. This seems to be a stronger assumption, but yeah, let's see. Yeah, I think it is fine because anyway this function is depending on the state and action pairs, and you could think of u of sa as again a supremum over t and t hat of d of f, t of sa, t of sa. This is set to u of sa. Yeah, maybe this is possible. So yeah, let's go forward. So yeah, this is from the previous lemma, and this is from this observation here. Yeah, so this one you can treat it as r tilde. So this is an equality. So yeah, now we get what the penalized MDP is after all. So penalized MDP M tilde is the tuple SA T, is it T hat? Okay, it's T hat and R tilde and gamma and other things if I have forgotten here. So yeah, this is the M tilde. And this equation 7 is also saying that return of from MDPM is greater than return of MDPM tilde. So yeah, so there are no constants as well. I mean, I was telling about constants if there are any, so there are no constants here. Yeah, so let's go further. Oh, okay. The algorithm seems really succinct. So let's see. Yeah, it's just saying r tilde is updated, run any RL algorithm until convergence to get. Okay, so this is like not a pure offline RL algorithm where you would just Based on the data set, you would just have the RL. I'll go to output di pi star. So here it is actually using pi star to further interact with the environment, or the simulator to get the actual optimal policy, I think. Yeah. So yeah, few of the papers concentrate on this, or yeah, one could as well extend it to this. Yeah, it depends on the application, what they want to solve. So yeah, let's see. Let's go further. Yeah, 4.2 section. I think here is where they bring out the balancedness property. So let's see. Yeah. Previously we didn't look at the increasing the lower bound, so maybe here we increase the lower bound, rm tilde, maybe. Let's see. So we will theoretically analyze. Okay, so here is one typo. So let's see. Pi star be the optimal policy on M. Pi b, the error is defined in this way, so that directly using the upper bound on the error. So yeah, so we observe that, on epsilon u of pi characterizes how ion is when pi is equal to pi b. Yeah, you expect the error to be very small. So like, okay, u of sa is small, so you expect epsilon u to be small. On the other end of the spectrum, if pi often visits outside of the batch data distribution, you expect the error estimates to be large. So u of sa is large. Okay. So yeah, I mean, the one could give the closed form expressions for how far away these two distributions would be, and yeah, you could actually characterize this epsilon u. So that would be, I think, a future work, maybe. Let's see. Yeah. So here, let's see. Delta min is defined in this way: min of epsilon u of pi let pi delta be the best policy incurring at most delta, which is defined in this way. So what this is saying is like, delta being smaller implies the distribution shift is smaller, but yeah, you have to balance such a way that delta is large enough I'm searching for a better pi star since the space increases. So yeah. So yeah, this is how the balancedness property comes from. Yeah, I still have a doubt of how this delta min comes into picture. I mean, trivial delta min would be 0. Yeah. or it could be thought of as an hyperparameter. Um, yeah, and are there any improvements? I'll go improvements based on delta min. I mean, no, future work question, I guess. So let's see. Yeah, this theorem is closing the arguments, I guess. So let's see. Using both of those assumptions, I mean the error bounds assumptions. Learned policy pi hat from the MOPO satisfies okay for all policies. The best policy in this is a lower bound for the pi hat, the MOPO algorithms return. So yeah. So since pi star, let's see. Yeah, let's go through this paragraphs a bit. The interpretation seems important. So for all delta greater than delta min, yeah. Yeah, this is true because epsilon u of pi was less than or equal to delta, and so this is true. So from 11, what I say is pi b, okay, is pi b in the search policy. But what are all the policies? Yeah, the interpretations say here, okay, from 11. Yeah, since pi b is in the search policy, we can conclude this one. So this suggests that pi hat should perform at least okay, as well as the behavioral policy. And yeah, this was small, so yeah, this seems to be good interpretation. So from 12, okay, 12 tells us pi hat is as good as any pi which is having error less than delta. So if the error is at most just delta, so yeah, I can conclude this. But the gap between the learned policy pi hat and pi star is still epsilon u of pi star. Yeah, characterizing this quantity would be a good idea for the further future work, or like a different draft for this paper. Yeah. Now the closer this distribution to the best data, pi star, okay, on the other hand, the smaller the uncertainty error of the dynamics is, okay. In the extreme case, you have, okay, we recover the optimal policy. So yeah, getting at least how far away so let me pose this question. As the iterations increases, is it possible that epsilon u of pi star decreases in some rate on k? Yeah, this would be a good contribution as well. So let's see. Let's go further. Yeah, the optimal choice of delta is achieved when balanced. So now more details of the algorithm is provided. It seems this is U of SA which they use. Yeah, makes sense because like the Frobenius norm of the transition probability matrix. This is the variance of the transition probability matrix. So yeah, would be interesting to change this to some other U of SA which will give equal or better results maybe. So yeah, firstly they parameterize using Gaussian processors and use Lipschitz regularization for their means. Yeah, other than that the short algorithm which they presented previously would complete this one. So practical implementations, I'll just go through this faster. I want to move to the results. So now yeah, as I said, UFSA is being used, I mean the Frobenius norm technique is being used for UFSA, and Lipschitz regularization. I think this one comes from Yao et al. The weights are normalized. Yeah, first as shown in the standard setting may improve in distribution, out of distribution, generalization. Okay. So and this is the heuristics. I mean for practical purposes, I guess. When true dynamics are not sufficiently Lipschitz is in some region will occur. Okay. Will incur larger error and uncertainty. Okay. Thus, these non-Lipschitz regions are heavily penalized. Okay, to avoid them. Yeah, we'll just move forward. Yeah, lambda is being the hyperparameter. So now, the experiments section. Let's see. It's they're denoting these better. Yeah, best achieved algorithm by the bold letters. So yeah, it seems the medium data set, the normal model free algorithms are offline. Model free algorithms are working better, but yeah, most of the other data sets, MOPO is working better than other things. So yeah, let's see what the description say. Oh, okay. These are divided into 3 sections. The first one is okay, standard, okay, which we saw in the table 1. The second one, out of distribution behaviors. Yeah, let's see section by section. Several baselines. Okay, bear is being used. Yeah, which we saw here. Bear, behavioral BRAC V and BRAC P. I think they are skipping BRAC V because the performance is very similar to BRAC V, I guess. So yeah, let's go forward. The first section is on comparing. Yeah, the table one which we already saw. So half cheetah hopper. The data sets are being generated from random rollouts. Medium, which is just termed from partially trained policies using SAC. Okay. Mixed is the policy which is being used from SAC until certain performance. Okay. Medium and expert, fully trained, partially trained policy. Okay. Rollouts from partially trained or random or okay. Oh, combining. Okay, okay. Yeah, combining these two, medium and expert data. Okay, so what they say here is our method is the strongest in mixed data sets and medium. Okay. Yeah, they also say that model based is performing less well in the medium data sets as we saw earlier. So fortunately the setting is one of which okay, yeah, model free methods can perform well. So there is some uh, improvements that can be seen in model free algorithms as well, which is not yet seen. So that is the open question here, I guess. So which I asked in the abstract. So let's see the second section to answer the question 2. So the out of distribution generalization. So let's see. Okay, there is a typo here. Okay, let's see the data. This validates MOPO is able to generalize to the okay. Are able to solve these problems. Even vanilla MBPO performs better than SAC into an okay. That's surprising. So MOPO, yes. Let's see. Concretely, we train SAC for 1 million, use the entire training replay buffer as trajectories for the batch data. Okay, then we assign these trajectories with new rewards. Okay, cheetah jump. Another typo to the okay. So this is just to achieve the out of distribution kind of scenarios. So yeah. So in these kind of data sets as well, MOPO is performing better. So which was one of the core parts of the theory. So core parts that the theory promised. So yeah, moving on to the third section. I hope this is the final one in this experiment section. So now note that no lab is no regularization, no ensemble methods of okay, no penalty, oracle uncertainty to okay, no direct usage of T minus TSA. Okay, this is the U of SA part. So yeah, this is where they have actually used it. So now Lipschitz regularization generally boosts the performance to both okay on both yeah, as we saw earlier. Or okay, this is being observed here, I guess. So let's see. This is the ideal performance oracles. So with Lipschitz regularization, these things are performing better. Yeah, but not in this set. So penalty, when you include penalty, then maybe Lipschitz regularization is not needed. So yeah, this seems to be the conclusion of this experiment section. So now moving on to the last section. Let's see. Existing model based algorithms outperform the vanilla model frame. So this phenomenon implies the model based RL has the ability to generalize. Okay, correct. However, online and offline algorithms must act differently when handling out of distributions. Okay. Model error on out of distribution drives exploration and corrective feedback in online setting can be detrimental when interaction is not allowed. Yeah, off policy algorithms are not good for offline data sets. So yeah. MOPO again performs state of the art RL in both standard benchmarks and out of distribution generalization. So yeah, now this work opens up number of questions and directions for future work. Let's see. First one is to future work to incorporate policy regularization ideas of into a reward penalty to improve narrow distributions, which is such as medium data sets. Okay. Second, it's an interesting theoretical question to understand why model-based methods appear to be much better suited for batch setting. Yeah, this seems to be the potentially good algorithms can be developed for model-based and model-free in certain kinds of data sets. Yeah, this seems to be a good direction to go into. So such as uncertainty. However, uncertainty estimation does not explain the entire. Okay, yeah. So better model free offline may be desirable. Yeah. So it is hopeful. We are hopeful that we'll get some model free offline RL algorithms for solving these offline RL problems. So let's see. Model based methods which would require further understanding where generalization benefits come from. Yeah. So yeah, the number of references are like, whoa, okay, 74. Yeah. Yeah, this is the end of this video. Hope you liked it. Yeah, look forward to the next video. Thank you. Have a great day.